Hello, my name is Professor Rad, and this is Precalc video 310, sinusoidal graphs, formulas. In this video, we'll be talking about what it means to be a sinusoidal function, and then we'll look at some formulas that help us identify particular features of those graphs, and then we'll do a couple of examples. This video is going to be the foundation for the next several videos because we're going to need to basically use these formulas sort of like a checklist when we go to graph trig functions moving forward. So let's start out by defining what it means to be a sinusoidal function. I've already gone ahead and put the definition in the oven, so it comes out fully complete here. So if you want to pause and copy that definition down, you can do that here. But basically, what a sinusoidal function is going to be is a function that looks like a transformation on either sine or cosine. So if you have a sine omega x minus phi, or if you have a cosine omega x minus phi, those are going to be our sinusoidal functions. And a, omega, and phi are all real numbers. And we also need omega to be positive. Now, we are using these Greek letters of omega and phi. So omega is the curly looking U, and phi is the almost Disney Y looking thing. So those will be the variables that we're using. When we transform a trig function or a sinusoidal function, that's going to have an impact on the amplitude and the period. So remember, the amplitude of a trig function, of a sine or cosine function, is going to be the distance from that like x-axis or from the middle of the function to either its topmost or bottommost point, right? So we're going from the middle to the extreme. So if we think about what multiplying by a is going to do to a sinusoidal function, it's going to take that function and it'll stretch it or it'll compress it by a. So for the amplitude, we're going to find the absolute value of a. Now, the reason we want the absolute value of a and not just a itself is because if a is a negative number, that will reflect the trig function. So our amplitude is always a positive number because it's representing a distance. So that's why we'll need the absolute value of a. The period, remember, is how often it takes before the trig function repeats itself. So a typical sine or cosine function, right? Like if you just have sine of theta or cosine of theta, that's going to have a period of 2 pi. It took 2 pi before the curve repeated. So when I look at the transformation here, the thing that's going to impact that is this omega that's in front of x, because the omega is either going to stretch or compress the trig function, right? That's the transformation that happens inside the function. So to account for that, I'm going to take my usual period, which is 2 pi, and we're going to divide it by omega to get the period of the transformed function. So dividing by omega is going to account for that transformed stretch or shrink. Then the third formula we have here is for the phase shift. What the phase shift is it's how much your trig function has been shifted to the left or the right. So to find the phase shift, we're going to do phi over omega. Now, the reason that we're dividing by omega here instead of just saying phi is because remember with your order of operations, with your inside transformations, they happen in sort of the reverse order of operations. So in order to account for that, we'll be dividing this value by the omega. All right, so these are our definitions. I do want to make a sort of side comment here about tangent and cotangent. So for the most part, we're going to be graphing transformations on sine and cosine. But if you are analyzing something like y equals a tan omega x minus phi, or y equals a cotan omega x minus phi, then the period is going to be just pi over omega. So the reason that the period for a transformed tangent or cotangent is pi over omega instead of 2 pi over omega is because the normal period for tangent or cotangent is pi instead of 2 pi. So that's why we'll be using this formula if we're looking for the period of tangent or cotangent function. If you're analyzing a secant or a cosecant function, then it's also going to be 2 pi over omega, because secant and cosecant have the same period as sine and cosine. All right, so oh, there's one more note I wanted to make before we did a couple of examples. So the note is, notice how omega has to be positive. So that won't always be the case, because sometimes you might have a reflection over the y-axis instead of just over the x-axis. So sometimes you might be presented with a trig function and you have omega being a negative value. So when that happens, so I'm just going to do a note. If omega is less than 0, then use even or odd properties to rewrite with a positive value for omega. So we'll make sure we do a couple of examples to do that, but remember that sine is an odd function and cosine is an even function. So we'll be using that information to help us rewrite, so we have an argument that has a positive omega. Once omega is positive, then we can determine these values here. All right, so let's do a few examples of applying these formulas and identifying the amplitude, the period, and the phase shift of some sinusoidal functions. Alrighty, so to help us complete this example, I've written down our important formulas and terms over here on this side. And as a reminder, for even an odd property, sine was odd. So that meant that sine of negative whatever is negative sine of whatever that was. And cosine is even. So cosine of negative thing is the same as just cosine of the thing. Okay? So we are going to get different results when we apply those properties, because one function is odd and the other one's even. So you want to make a note of that. Now for this example, we're going to determine the amplitude, period, and phase shift for each of these 3 functions. So let's dig in. We'll do example A and go about our way. So the first thing that I look for when I'm analyzing a sinusoidal function is I want to ensure that the coefficient of x is positive. In other words, I need to make sure omega is positive. So check for a positive coefficient of x. Everything else, it doesn't matter whether it's positive or negative. We need omega to be positive. So when I look at this function f of x, the coefficient of the x is a -3. So I don't like that. So I need to change that. So what I'm going to do is I'm going to apply this even odd property here to rewrite it so that I have a positive x. So let's rewrite f of x here. So f of x is sine of pi minus 3x. So what I'm going to do in order to get this to be positive, I'm going to factor a -1 out of the parentheses. So that's going to be sine of negative pi plus 3x. Right? So if I distribute that negative sign, I get pi, and if I distribute it here, I get minus 3x. Now I have this in the form sine of negative whatever. So from our odd property, sine of negative whatever is negative sine of the whatever. So this is going to be negative sine of negative pi plus 3x. Now it's also traditional to write the x portion first. So I'm just going to use the commutative property and rewrite this as negative sine of 3x minus pi. So before I go ahead and do any finding of the amplitude, period, or phase shift, I need to know to do this check first and create a positive omega, or rewrite it with a positive omega if it was started out negative. So these functions are all equivalent. If I go to graph them, I'm going to get the same function. So this now is the function that I'm going to be analyzing. So when I state my values for omega, a, and phi, I'm going to be using this function. So let's do that. So we have A, omega, and phi. A is going to be our coefficient of the whole trig function. So because there's a negative on the outside of this function now, A is going to be -1. Omega is our now positive coefficient of x, so that's going to be 3. And in our formula, so we had A sine omega x minus phi. So notice that we're subtracting phi, not adding it. So that means phi is going to be pi. So just like when we were analyzing our quadratic functions, right, when we had to find the vertex of it, we knew that we had hk as the vertex of the parabola, and the h was on the inside of that squaring, and it had to be the opposite sign. That's what's going on here. So we have the opposite sign for phi because it's an inside transformation. So that's going to continue to plague us. When you have inside transformations, they're always the opposite. It's infuriating a little bit. So now we've got these values. Once you have these values, you can apply those formulas to identify the values. So the amplitude is the absolute value of A. So our amplitude is the absolute value of -1. So we're going to get 1. The period is 2 pi over omega. So in this case, omega is 3. And sometimes you may need to simplify that expression. In this case, 2 pi over 3 is as simple as it gets. So that's our period. And then the phase shift is phi over omega. So the phase shift is going to be phi, which is pi, over omega, which is 3. There we go. So let's erase this and we'll work through a second example together. If you want to try part B on your own first and then see how you do, you can do that. You can pause the video and work through it. But if you're like, I need another example to feel solid on this, we can work through part B together. For part B, we have g of x is equal to -6 cosine of pi/4 x plus pi/3. So I've rewritten that over here. We're going to do our first check to make sure the coefficient of x is positive. So when I look at the coefficient of x, this time it's a positive pi/4. So we're going to get a positive omega. So we don't have to worry about those even odd properties for this one. Also, don't let the fact that there's pi involved trouble you. Remember, pi is like 3.14, so pi is like 3, basically. So when you see pi/4 x, you could think of that as like, that's just like 3/4 x. And pi over 3, that's just a little bit bigger than 1. They're just numbers. So don't let the pi cause you to think this problem is going to naturally be challenging. It's not. It's just going to be, you know, what it is. So since we have a positive omega here, we can list out our values for A, omega, and phi. So A is the coefficient of the whole trig function. So A is -6. Omega is our coefficient of x. So that's pi/4. And phi, remember, phi is being subtracted. So we have to change the sign. So in this example, phi is going to be a negative pi/3. Once we have those values, now we can apply our formulas. So the amplitude is going to be the absolute value of A. So this is the absolute value of -6, since that was our value for A. And we'll get a +6. The period is going to be 2 pi over omega. Oh, yuck. So omega is pi over 4. So I'm going to get a complex fraction here. 2 pi over 4. So of course, we don't want to leave our answer as a complex fraction. So let's go ahead and multiply the top and bottom by 4. so that these 4's cancel out, and I'll get 8 pi over pi. Oh, and then our pi's cancel out. So for the period, we just end up getting that t is equal to 8. Now this is kind of strange because remember when we go to graph sine or cosine or any of our trig functions, we typically index that horizontal axis in terms of pi, right? We count out pi halves, pi, 3 pi halves, 2 pi, and so on. So what this is telling us is because omega was pi fourths, when we go to label our x-axis, we don't want to index it in terms of pi because that omega is essentially removing it from our indexing for our function. So we'll be talking about how that'll apply in the next set of videos, but just know that that's going to be a thing. So a little foreshadowing here. And then we'll also do the phase shift. So our phase shift is phi over omega. So phi is negative pi over 3. And omega was pi over 4. Okay, I'm going to need more space in the tiny corner over here. So what I'm going to do is I'm going to rewrite this using division. So I've got negative pi thirds divided by pi over 4. And then this will be negative pi over 3 times 4 over pi. So our pi's cancel and we get negative 4 thirds. So our phase shift is going to be negative 4 thirds. Here's what this means. Okay, so again, I'm going to do a little bit of a preview for what's to come. But what this means, because this is a transformation on cosine, cosine normally starts up at 1 and comes down like this, right? So what the phase shift means is instead of starting at the point 0, 1, we're going to shift that x value to negative 4 thirds. So here we would be at negative 4 thirds, and that's where this point is going to be. And then we'll use the other information to figure out where the other points should land. Okay, so the period is going to help us determine how this will stretch, and the amplitude will determine how much it stretches vertically. And the phase shift is going to give us where we start. So then it'll be kind of going down, right, doing its usual cosine thing. But it's just a little preview of what's to come, but we'll worry about that in the future. So for the present, let's worry about part C. So for this one, do try this one on your own. See if you've got everything kind of figured out. I'm going to move out of the way so that if you want to pause the video here, you can see both example C and all our nice formulas. So I'm going to pause and write my answers on the board. You're going to pause, write your answers on paper, and then compare. Alrighty, so how did we do with part C? So the first thing I noticed with part C was that I had a negative coefficient for x. So because cosine is even, I could rewrite it as just 2 cosine of 4x. So with sine, that negative that was on the inside resulted in a new negative being on the outside because sine is odd, but cosine is even. So that negative on the inside, if I wanted to get rid of it, I just can because we're symmetric about the y-axis. So if we did a horizontal reflection, no change. So then I determined my values for A, omega, and phi. A is a positive 2, omega is 4, and there is no shifting. We just have 4x. So phi is 0. So that means our amplitude is 2. Our period is going to be pi halves, and the phase shift is going to be 0. All right, so that's it for these formulas and for these examples. In the next, I think it's 3. No, I think it's 3 or 4 videos. We're going to be applying these definitions to either writing the equation of a sinusoidal function, that's what we'll be looking at in the next video, or graphing sinusoidal functions. So I'm looking forward to seeing you in those videos. In the meantime, I hope you have a wonderful day. Bye for now.